In 1609, Galileo Galilei raised a newly improved telescope toward the night sky from northern Italy. The instrument was small, awkward, and primitive by modern standards, yet it magnified distant objects roughly 20 times. Through that narrow tube, you could suddenly see a moon covered with shadows, bright ridges, and irregular landscapes. Soon, 4 tiny points of light appeared near Jupiter, changing position from one night to another. Something was orbiting another world. But Galileo was arriving very late, long before telescopes, observatories, mathematics, or even written language. Human beings had already spent countless generations beneath the stars to understand how you eventually discovered the universe. You must travel backward beyond Galileo, beyond Rome and Greece, and beyond the first cities. You return to a much quieter night. Imagine standing outside thousands of years before the first astronomical books were written. There are no electric lights on the horizon, no aircraft blink overhead, no satellites quietly cross the darkness. The night belongs entirely to the sky. You feel cooling earth beneath your feet as daylight disappears. Smoke from a nearby fire carries the smell of burning wood and cooked food. Somewhere beyond the light, insects pulse through the grass, while distant animals call from unseen places. Above you stretches something overwhelming. Thousands of stars are visible to the naked eye under sufficiently dark conditions. The Milky Way forms a pale, irregular band across the heavens, much brighter than most modern city dwellers ever experience. You do not know it is a galaxy. You have no reason to imagine that those faint lights might be distant suns. You cannot know that many contain the same elements eventually found within your own body. You simply see the sky, yet the longer you watch, the less random it becomes. Stars rise from one part of the horizon and eventually disappear elsewhere. Familiar patterns return night after night. The moon changes shape gradually, vanishes into darkness, then begins another cycle. The sun behaves differently across the seasons. Its rising position slowly shifts along the horizon. Days lengthen and shorten. Certain stars disappear for months before returning at familiar times. For communities dependent upon hunting, migration, crops, or seasonal resources, these patterns matter deeply. The heavens become more than decoration because they offer a vast natural clock. You begin remembering. Perhaps an elder recognizes that one bright group of stars appears before a particular seasonal change. Another pattern becomes associated with migrating animals or changing weather. No surviving voice can tell you exactly when humans first recognized such relationships. Archaeologists therefore work with indirect evidence, including monuments, artifacts, markings, and the orientations of ancient structures. Scholars continue debating which prehistoric objects represent deliberate astronomical records and which interpretations project later knowledge onto ambiguous evidence. The uncertainty matters. Human curiosity probably developed gradually, rather than beginning with one forgotten astronomer pointing dramatically upward. Generations simply watched, remembered, compared, and passed observations onward. Some evidence is especially intriguing. At Nabta Playa in southern Egypt, prehistoric communities constructed stone arrangements thousands of years before the Great Pyramids. Researchers have proposed astronomical interpretations for parts of the site, including possible relationships with seasonal solar positions. Exactly how sophisticated those astronomical intentions were remains debated. Elsewhere, ancient monuments eventually became aligned with striking celestial events. At Stonehenge in southern Britain, major architectural features correspond with important solar directions around the solstices. Yet you should resist imagining a prehistoric scientist carrying a clipboard between the stones. The sky was woven into practical life, ceremony, memory, identity, and probably stories whose original meanings are largely lost. That mixture feels strange only from a modern perspective. For most of human history, astronomy was never isolated neatly from agriculture, religion, navigation, politics, or storytelling. Watching the heavens could tell you when seasons changed, while also connecting your community with ancestors and sacred traditions. Then something alarming happens. The moon begins disappearing. You watch a dark shadow slowly cross its familiar face. The brightness fades, while the surrounding night seems unusually attentive. Without astronomical theory, a lunar eclipse can feel less like geometry and more like a disturbance in the natural order. A solar eclipse is even more unsettling. Daylight weakens unexpectedly. The air cools against your skin. Shadows become peculiar. Animals may alter their behavior, and the familiar sun seems to be consumed. Then the light returns. Repeated experience gradually reveals that even frightening celestial events belong to patterns. That recognition becomes one of astronomy's deepest foundations. Nature can surprise you, but careful observation sometimes allows surprise to become prediction. Other lights behave differently. Most stars maintain recognizable arrangements relative to one another, yet a few bright objects wander slowly against that background. You know them today as planets. To an early observer, however, their movements are wonderfully peculiar. Some travel steadily across the stars, then appear to slow, reverse direction, and later continue forward. Mars can become particularly striking. Its reddish appearance distinguishes it from many surrounding stars, while its wandering path refuses to behave like the fixed patterns nearby. Venus can blaze brilliantly near sunrise or sunset, disappearing and returning according to its own rhythm. The heavens are orderly, but not simple. Gradually, generations create stories to remember what they observe. Constellations become hunters, animals, heroes, tools, spirits, and other familiar shapes, depending upon the culture looking upward. There is no single ancient sky. Different societies divide the same stars into different pictures and meanings. The physical heavens remain overhead, while human imagination creates many cultural maps across them. Even so, practical knowledge accumulates. You can use stars to recognize directions. Lunar phases provide convenient units of time. Solar motion helps mark seasons. Repeated celestial cycles allow communities to anticipate changes that once seemed mysterious. The sky becomes memory written in light. There is a quirky possibility hidden within this long relationship. Some researchers investigate whether extremely old oral traditions might preserve memories of unusual astronomical events or changing celestial conditions. Such claims require considerable caution. Stories transform as generations retell them, making direct connections between ancient myths and specific astronomical events difficult to demonstrate. Still, the possibility reminds you how deeply the night sky can settle into collective memory. Eventually, watching becomes recording. Settlements grow into towns, and towns become cities. Agriculture produces surpluses. Administrators count grain, animals, workers, and days. Writing emerges in several regions of the ancient world. Now, a celestial observation no longer needs to survive only inside one person's memory. A pattern can be marked, stored, copied, compared, and examined by someone born generations later. That changes everything. In Mesopotamia, observers will eventually create extraordinary records of celestial events. Their work will transform repeated watching into systematic astronomy and make increasingly sophisticated predictions possible. But you have not reached those tablets yet. For now, remain beneath the older darkness. The fire beside you has weakened. Its warmth barely reaches your hands, and the smell of smoke has softened in the cool night air. Above, the Milky Way remains immense. You cannot measure its distance. You cannot know its age. You cannot imagine galaxies beyond it, expanding space, invisible matter, or the ancient radiation left from a hotter cosmic past. None of those ideas exist yet, and perhaps that makes this moment more important, not less. Every observatory, telescope, equation, spacecraft, and cosmological model begins with the same simple human action you are performing now. You look upward, you notice that something returns. You remember where it was. Then, on another night, you look again. Across generations, those small acts of attention begin accumulating into knowledge. The universe has already existed for billions of years, but one small species on one ordinary world is beginning to recognize patterns in its light. Soon, those patterns will be written down, and once the sky becomes a record, rather than only a mystery, humanity can begin measuring the heavens. Thousands of years later, the same stars still turn above you, but the world beneath them has changed. You now stand near the great rivers of Mesopotamia, where growing cities rise from broad plains. Mud brick walls hold back heat during the day, while narrow streets collect the smells of bread, animals, smoke, and river mud. At night, the temperature falls. You climb above the crowded streets, where the horizon opens beneath a remarkably dark sky. The constellations remain familiar to generations of observers, but watching them has become something increasingly systematic. Someone is keeping records. By the first millennium BC, Babylonian scholars were compiling extensive observations of the moon, planets, eclipses, and unusual celestial events. Their surviving clay tablets reveal an astronomical tradition built through repeated measurements across generations. This is a quiet revolution. You no longer depend entirely upon memory or stories passed from one observer to another. A scribe can press information into wet clay, allowing someone decades later to compare tonight's sky with an earlier one. The clay feels cool before drying. A reed stylus presses small wedge-shaped marks into its surface while oil lamps flicker nearby. Outside, sandals scrape against packed earth, animals shuffle in courtyards, and voices gradually disappear as the city settles. Above everything, the observations continue. Babylonian astronomers become especially skilled at recognizing repeating celestial cycles. They monitor lunar phases and eclipses while following the complicated movements of visible planets against the background stars. Their purpose is not identical to modern astronomy. Celestial events can carry political and religious significance, particularly for rulers and kingdoms. An eclipse might therefore be interpreted not simply as a predictable alignment, but as a possible omen requiring careful attention. Observation and divination coexist. From your modern perspective, separating them might seem obvious. For the Babylonian scholar, however, accurate prediction can strengthen the interpretation of celestial signs rather than weaken it. This helps explain why careful records become valuable. The more observations accumulate, the easier it becomes to recognize recurring patterns. One particularly important relationship involves eclipses and a cycle lasting a little more than 18 years. Today, this is commonly called the Saros cycle. Ancient observers recognized useful eclipse repetitions long before modern gravitational theory explained why they occurred. Prediction, therefore, becomes possible without understanding the complete physical mechanism. That distinction will follow astronomy for centuries. You can sometimes describe what the heavens will do before knowing why they behave that way. Babylonian mathematical astronomy eventually becomes remarkably sophisticated. Scholars develop numerical procedures for predicting lunar and planetary phenomena without constructing the physical universe imagined by later Greek philosophers. The sky becomes something calculable, yet uncertainty surrounds important details of this intellectual world. Scholars still debate how particular mathematical techniques developed and how knowledge moved between different communities over long periods. Surviving tablets provide only fragments of a much larger tradition. Many records vanished. Others remain damaged. Some practices probably existed orally alongside written methods that happened to survive. History reaches you unevenly. Far southwest of Mesopotamia, another relationship with the heavens develops beside the Nile. Imagine standing in ancient Egypt before sunrise. The air smells of damp soil and vegetation near the river. Beyond the cultivated land, desert stretches outward beneath a sky beginning to brighten. The Nile shapes almost everything around you. Its seasonal behavior influences agriculture, transportation, taxation, settlement, and political power. Keeping track of time is therefore practical as well as ceremonial. The sky helps. Ancient Egyptians developed calendars connected with solar and seasonal cycles. The appearance of certain stars also becomes associated with important moments during the year. Sirius is especially famous. Its annual reappearance in the morning sky became connected with Egyptian calendrical traditions and the season surrounding the Nile's inundation. Although the precise relationships changed across centuries and locations, nothing remains perfectly fixed. Calendars drift, administrative systems change, religious traditions evolve. Even the sky itself shifts slowly over immense periods because Earth's rotational axis changes direction through precession. You would never notice that movement during one lifetime. Across many centuries, however, stellar positions relative to seasonal dates slowly change. The heavens appear permanent, yet careful observation reveals that even their familiar arrangement is not entirely timeless. Egyptian monuments also demonstrate celestial awareness. Some temples and monumental structures possess orientations connected with solar or stellar directions. Yet historians must be cautious before assigning astronomical meaning to every impressive alignment. Ancient builders had many concerns: landscape, ritual, politics, architecture, local geography, and celestial symbolism could overlap. A building pointing toward a meaningful horizon does not automatically make it a scientific observatory in the modern sense. Still, the sky clearly mattered. You can imagine a priest or timekeeper watching selected stars during the night. Darkness surrounds the temple walls, while footsteps echo faintly across stone. The observer waits patiently. Certain stellar patterns can help divide nighttime into intervals. Time is no longer only something felt through hunger, fatigue, daylight, or changing shadows. It can be organized through the heavens. One curious surviving feature of Egyptian astronomy involves groups of stars now called decans. These were used in systems for marking portions of the night and became important within calendrical and religious contexts. A star could become a clock. Not a convenient clock, admittedly. Clouds remain troublesome, and nobody has provided you with a glowing bedside display. Still, the principle is profound. Regular motion in the heavens can measure passing time on Earth. Other civilizations make related discoveries independently or through complex exchanges of knowledge. Across different regions, people observe solstices, lunar cycles, planetary motion, and the seasonal appearance of stars. Their interpretations differ greatly. The sky might be understood through divine beings, ancestral traditions, mathematical patterns, political omens, or combinations of these ideas. You should not imagine a straight road toward modern science. Knowledge develops through branching paths. Useful observations can exist beside ideas later abandoned, while sophisticated mathematics can emerge inside cosmologies completely different from your own. This is how understanding usually grows. Humans rarely discard an entire worldview overnight because one new measurement appears. New information must compete with traditions that already explain much of ordinary experience. And ordinary experience strongly suggests something obvious. Earth feels still when you stand beside the Nile or beneath the Mesopotamian stars. You do not feel the ground racing around the sun. You see the sun cross the sky, while the stars appear to rotate around you. A stationary Earth seems entirely reasonable. Soon, thinkers around the Mediterranean will begin asking whether appearances reveal physical reality. They will use geometry and philosophy to construct increasingly elaborate pictures of the cosmos. Some will place Earth firmly at its center. One remarkable thinker will suggest something radically different before that argument can appear. However, humanity needs to make another conceptual leap. Predicting celestial patterns is no longer enough. You begin asking what the heavens are made of. You wonder how far away they might be. Most unsettling of all, you begin asking whether Earth occupies the privileged position that your senses seem to promise. The clay tablets behind you have already made the sky measurable. The next generation of questions will attempt something more ambitious. Humanity will try to build a universe. The records continue accumulating, while another kind of question begins taking shape around the Mediterranean world. You are no longer satisfied with knowing when Mars will appear or when the moon might darken. You want to understand what these objects are, how they move, and what kind of structure could contain them. The question sounds simple. It is anything but simple. You walk through a Greek settlement beneath a warm evening sky, hearing sandals against stone and conversation drifting from nearby courtyards. Olive oil lamps burn with a faint smell, while the last sunlight fades from pale walls. Overhead, the familiar heavens return. The stars seem attached to a vast surface surrounding you. The moon travels across that background, while the wandering planets follow their more complicated paths. Earth, meanwhile, appears completely motionless. You feel solid stone beneath your feet. Trees are not being swept sideways by some tremendous invisible wind. A dropped object falls downward rather than being abandoned behind a moving planet. Placing Earth at rest seems sensible. Yet Greek thinkers increasingly attempt to explain nature through geometry, reasoning, and physical principles rather than relying exclusively upon traditional stories. There is no single Greek model. Ideas compete, change, borrow from older traditions, and sometimes disappear almost completely. What survives in later texts represents only part of a much larger intellectual conversation. Some early thinkers imagine Earth in forms that would seem peculiar today. Others propose different arrangements for the sun, moon, planets, and stars. Gradually, spherical models become influential. By the 4th century BC, Aristotle presents arguments supporting a spherical Earth. One especially elegant clue comes from lunar eclipses. During such an eclipse, Earth's shadow falls across the moon. The shadow appears curved. A sphere naturally produces a circular shadow from every direction, making this observation useful evidence for Earth's shape. There are other clues. Travel north or south, and different stars become visible above the horizon. Familiar constellations change their altitude, suggesting that observers occupy different positions on a curved surface. The Earth becomes a globe. This does not mean it moves. Aristotle develops a cosmos in which spherical Earth remains stationary near the center. The heavens belong to a different physical order, with celestial motions associated with enduring circular patterns. Circular motion possesses philosophical appeal. A circle has no obvious beginning or ending, making it seem suitable for eternal celestial behavior. Meanwhile, earthly objects appear to move toward their natural places. Heavy material falls downward. Flames rise. You can understand why such ideas feel persuasive when modern mechanics does not yet exist. Aristotle is trying to construct a coherent physical system from the evidence and concepts available around him. His influence will become enormous, yet even during antiquity, Earth-centered thinking is not the only possibility. In the 3rd century BC, Aristarchus of Samos proposes something astonishing. According to surviving ancient reports, he places the sun at the center, while allowing Earth to rotate and travel around it. You have encountered heliocentrism nearly 18 centuries before Copernicus, but the idea does not conquer astronomy. Why should it? Imagine standing outside and being told that Earth is spinning while simultaneously rushing around the sun. Nothing beneath your sandals appears to support such extraordinary motion. There is another serious difficulty. If Earth moves around the sun, nearby stars should appear to shift slightly against more distant stars as your viewing position changes during the year. This effect is stellar parallax. Ancient observers cannot detect it. The correct explanation is that stars are enormously farther away than their instruments can establish, but without measurable parallax. A moving Earth requires a universe much larger than many people expect. That is a substantial price. Aristarchus is remembered for another remarkable attempt involving celestial distances. Using geometry, he tries to estimate the relative sizes and distances of the sun and moon. His observational measurements are not precise enough. Still, the method matters. Instead of merely declaring the heavens unreachable, you can use angles observed from Earth to infer properties of distant objects. Geometry becomes a ladder into space. Around the same broad period, Another famous calculation demonstrates just how powerful that ladder can become. Eratosthenes estimates Earth's circumference. Imagine yourself in Egypt around the 3rd century BC. Sunlight falls strongly across stone, while heat rises from the ground and dry air presses against your skin. Eratosthenes knows of observations associated with Siena, near modern Aswan, around the summer solstice. The midday sun there appears extremely high. At Alexandria, a vertical object casts a measurable shadow. The difference in solar angle between the locations can be combined with their approximate separation from that information. Earth's circumference can be estimated through geometry. The result is remarkably close, depending upon how the ancient units are interpreted. Historians continue discussing details of the measurement, including the exact length represented by the unit used and how accurately the distance between locations was known. Even with those uncertainties, the conceptual achievement remains extraordinary. You can measure an entire planet without walking around it. You need sunlight, distance, geometry, and patience. The universe is becoming accessible through indirect measurement. Then comes Hipparchus. Working during the 2nd century BC, Hipparchus becomes one of antiquity's most accomplished astronomical observers and mathematicians. He develops influential methods for describing celestial positions and motions. Ancient sources also associate him with a major catalogue of stars. You begin mapping the heavens numerically. A star is no longer only part of a mythological figure. Its location can be measured relative to a coordinate framework and compared with observations from another period. This leads toward a subtle discovery. Hipparchus compares stellar positions with earlier observations and recognizes that the celestial coordinate system connected with the seasons appears to shift slowly. Earth's axis is changing orientation. You know this phenomenon as axial precession. One complete cycle takes roughly 26,000 years, far beyond any individual lifetime. Yet careful records allow you to detect motion too slow for any single observer to witness directly. Time itself becomes an instrument. There is also a wonderfully human problem hiding inside ancient star catalogues. Exactly which surviving catalogue traditions preserve Hipparchus's original work has occupied scholars for centuries. Modern examinations of ancient manuscripts have occasionally produced new evidence, reminding you that astronomy's history can still change through discoveries made in old texts. Even lost observations can leave shadows. Meanwhile, planetary motion remains stubbornly complicated. Mars sometimes moves eastward against the stars, slows, reverses, and later resumes its usual direction. Other planets display related behavior. You watch this happen over successive nights. If celestial motion should be orderly and circular, how can wandering planets perform these strange loops? Mathematicians develop combinations of circular motions to reproduce what observers see. These techniques will eventually become central to one of antiquity's most powerful astronomical systems. That system will be associated with Ptolemy. It is tempting to imagine that ancient geocentrism survives because nobody questions it. The reality is more interesting. Earth-centered models survive because they match ordinary experience and can be made mathematically useful. They also avoid physical problems that a moving Earth seems to create. A successful model does not need to be ultimately correct to be impressive. That lesson will return repeatedly. You step outside again as the Mediterranean night deepens. Sea air carries the smell of salt, while distant voices fade behind you. Mars glows above the horizon. You now inhabit a spherical Earth whose circumference can be estimated. The stars can be catalogued. Celestial distances can at least be approached geometrically. Yet Earth still rests near the center. Soon, circles will be placed upon circles with extraordinary mathematical skill. Predictions will improve. Tables will spread. And one ancient model will become so useful that it survives for more than a millennium. The heavens are becoming a machine, and humanity is preparing its first great mathematical blueprint. By the 2nd century A.D., generations of observations have turned the night sky into an enormous mathematical puzzle. You find yourself in Alexandria, one of the ancient Mediterranean world's great centers of learning. The city carries the smell of sea air, cooking fires, animals, and crowded streets warmed throughout the day. After sunset, the heavens seem wonderfully calm, yet the planets refuse to behave simply. Mars is particularly troublesome. Night after night, you can measure its position against the background stars and watch it move gradually across the sky. Then something peculiar happens. Mars slows. For a time, it appears to reverse direction before eventually turning again and continuing along its earlier path. Jupiter and Saturn display similar retrograde motion, while Mercury and Venus present complications of their own. Any successful astronomy must explain these wanderings. Claudius Ptolemy works within a mathematical tradition already centuries old. He does not simply invent geocentrism, nor does he create every mathematical device later associated with his system. Instead, he inherits and develops earlier ideas. His great astronomical work gathers observations, geometry, star positions, planetary models, and computational methods into an exceptionally influential framework. Earth remains near the center. Around it travel the Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and the sphere of distant stars within the traditional ordering. But their mathematical motions are not merely simple circles around Earth. To reproduce planetary appearances, astronomers use combinations of circular movements. A planet can move around a smaller circle whose center travels along a larger path. The smaller circle is called an epicycle. Imagine drawing a large circle on parchment. Then place a smaller rotating circle upon its circumference and let the planet travel around that smaller path. Suddenly, looping motion becomes possible. From Earth, the resulting path can resemble the strange backward movement you observe in Mars. Geometry transforms an apparent celestial irregularity into something predictable. Ptolemy's models become more sophisticated still. The Earth can sit slightly away from the exact center of a planet's larger circular path. Another mathematical device, later called the equant, helps reproduce changes in observed planetary speed. The result is not aesthetically simple. It is useful. That distinction matters, because later retellings sometimes portray ancient astronomers as desperately adding meaningless circles to rescue an obviously failing theory. The historical reality is subtler. Ptolemaic astronomy produces predictions good enough for many practical purposes. It organizes substantial observational knowledge within a mathematical framework that trained astronomers can actually calculate. You can create planetary tables. You can estimate celestial positions. You can predict certain astronomical phenomena with increasing reliability. Without telescopes or modern physics, this is an impressive achievement. The model also agrees with something your body tells you constantly: Earth does not seem to move. Stand beside a quiet pool. You feel no enormous rotation beneath your feet. You experience no obvious motion carrying the entire world around the sun. When you throw an object upward, it falls near you. The stars appear to circle overhead. Why abandon all of that? A moving Earth would require explanations that ancient physics cannot easily provide. It would also demand immense stellar distances because observers still detect no annual stellar parallax. The geocentric universe therefore remains reasonable. That does not mean everyone agrees about its physical reality. Ancient astronomy contains an important distinction between mathematical models that predict appearances and physical descriptions claiming how celestial machinery truly works. Scholars still discuss exactly how Ptolemy himself understood that relationship. Was every geometrical device meant to represent physical structures in the heavens, or were some primarily mathematical tools? The surviving texts leave room for interpretation. That uncertainty is valuable because it prevents you from turning historical astronomy into a simple contest between intelligent people and foolish ones. People are working with incomplete evidence, just as you are today. Ptolemy also preserves a substantial catalogue of stars, building upon earlier astronomical traditions. Their positions and brightnesses help transform the night into an ordered celestial geography. There are quirks within that catalogue. For centuries, historians have debated how much of Ptolemy's stellar information derives from Hipparchus and how much reflects independent observation or later transformation. The argument continues because ancient data rarely arrive with convenient laboratory notes. You inherit fragments. Still, the catalogue becomes enormously influential. Imagine copying numerical tables by hand under weak lamplight. The smell of oil hangs in the room while your fingers brush rough writing material. One mistake can migrate into another copy, yet the knowledge survives. Centuries pass, empires change, languages of scholarship shift, institutions rise and disappear, and political borders repeatedly move across the old Mediterranean world. The planets continue their wandering regardless. Ptolemy's astronomy survives because scholars preserve, translate, teach, criticize, and improve it. The system becomes embedded within traditions, extending far beyond the society that produced it. Meanwhile, ordinary people continue seeing essentially the same sky. A farmer does not need an epicycle to notice the moon's changing phases. A sailor can use familiar stars for orientation. Calendars remain connected with celestial cycles. Religious observances in many societies depend upon astronomical timekeeping. Rulers and administrators also require calendars capable of organizing taxation, agriculture, ceremonies, and civic life. Astronomy remains practical. It is also philosophical. If Earth rests at the center of the cosmos, what does that position mean? Modern imagination sometimes assumes that being central must automatically mean being honored. Ancient and medieval interpretations are considerably more complicated. The center can represent heaviness and change rather than perfection. The heavens may be considered more regular than the corruptible earthly realm below them. Cosmic geography, therefore, cannot be reduced to a simple claim that humans considered themselves physically important. History enjoys ruining convenient summaries. As centuries move forward, Ptolemaic astronomy becomes increasingly connected with other intellectual traditions. Scholars working in the Islamic world will encounter Greek astronomical texts through translation and study. They will not simply place them on shelves. They will calculate. They will observe. They will identify problems. From cities stretching across a vast scholarly network, astronomers will refine measurements, develop instruments, construct new tables, and question aspects of inherited planetary models. Some objections will become mathematically profound, yet the geocentric framework will remain resilient because replacing a successful system requires more than finding imperfections. You need something better. That replacement has not arrived. For now, imagine standing beneath a late ancient sky as Saturn moves almost imperceptibly among the stars. Somewhere nearby, calculations predict where it should appear weeks or months later. The prediction will not be perfect, but it works. Humanity has achieved something remarkable. The heavens, once remembered mainly through seasonal patterns and stories, can now be represented through a mathematical architecture extending far beyond Earth. The architecture is ultimately mistaken in important ways, yet it preserves observations, creates questions, and gives later astronomers something precise enough to challenge. That is how knowledge often advances. A useful model survives until accumulated evidence and a stronger alternative begin revealing where its foundations fail. The next transformation will not begin with someone casually declaring that the ancients were wrong. It will unfold through centuries of careful work. Across medieval observatories and centers of learning, astronomers will measure the same wandering planets again, and with every improved measurement, the old celestial machine will become just slightly more uncomfortable. Centuries pass, and the mathematical heavens, inherited from antiquity, travel farther than their creators could have imagined. You move eastward and southward through a changing world, entering cities connected by trade, scholarship, pilgrimage, government, and correspondence. Books and ideas move between communities, although never as smoothly as a simple historical timeline might suggest. Ancient astronomy survives through human effort. Texts must be found, translated, copied, taught, corrected, and sometimes reconstructed from incomplete manuscripts. Knowledge can disappear surprisingly easily when libraries burn, institutions weaken, or languages cease being widely understood. Yet astronomical traditions continue, from roughly the 8th century onward. Scholars working across the Islamic world translate and study important Greek scientific works alongside knowledge inherited from Persian, Indian, and other traditions. Ptolemy becomes particularly influential. His mathematical astronomy provides an extraordinary foundation, but inherited authority does not prevent examination. Astronomers compare predictions with observations and investigate places where theory becomes physically or mathematically uncomfortable. You can picture the work at night. The heat of the day fades from stone walls while cooler air settles across an observatory courtyard. Oil lamps produce a faint, smoky smell, but they must remain distant enough to preserve your dark, adapted vision. Metal instruments feel cool beneath your fingers. There is still no telescope. Everything depends upon naked-eye observations assisted by increasingly refined instruments, careful geometry, accurate clocks where available, and generations of mathematical experience. One important center emerges in 9th century Baghdad. Under Abbasid patronage, scholars conduct astronomical work connected with translation, mathematical research, and observations. Measurements of celestial positions and Earth's dimensions become part of a broader scientific culture. The Earth is still treated as spherical by learned astronomers. This deserves emphasis because modern popular culture sometimes imagines medieval people universally believing in a flat Earth. That picture is misleading. Educated astronomical traditions across much of the medieval Islamic world and Christian Europe generally inherited a spherical Earth from antiquity. People could still disagree about geography and cosmic structure, but the planet's roundness was hardly a forgotten secret waiting for a Renaissance sailor to rediscover it. The medieval sky remains geocentric. The sun crosses overhead. The planets wander against distant stars, and mathematical models attempt to describe their paths around a stationary Earth. Yet measurements improve. Around the late 10th and early 11th centuries, the astronomer Al-Biruni develops sophisticated work involving geography, mathematics, and astronomy. He discusses methods capable of estimating Earth's dimensions through observations and geometry. Again, you find yourself measuring something enormous without physically crossing it. The old lesson returns. Geometry reaches where your body cannot. Other astronomers refine planetary parameters and create tables useful for predicting celestial positions. These tables can support calendars, timekeeping, astrology, navigation, and religious requirements involving direction and time. The motivations overlap. Modern categories do not always fit comfortably. A scholar interested in planetary prediction might move between mathematical astronomy and astrology without experiencing the sharp boundary you would expect today. Accurate observation remains valuable either way. Then the buildings themselves become larger. In the 13th century, a major observatory is established at Moraga in present-day Iran under the patronage of Hulagu Khan. Imagine approaching the complex when evening cools the surrounding landscape. You hear low conversation among scholars and assistants. Paper rustles. Metal instruments shift gently, while distant animals and footsteps punctuate the quiet. The observatory gathers expertise and equipment on an impressive scale. Astronomers associated with Moraga investigate mathematical alternatives to troublesome features within Ptolemaic planetary theory. Nasir al-Din al-Tusi develops a geometrical construction now known as the Tusi couple. It is wonderfully clever. Two circular motions can combine to generate an oscillating linear motion. The construction provides mathematicians with new ways to reproduce celestial behavior while maintaining preferred forms of circular motion. This sounds abstract, yet it reveals something important. Medieval astronomers are not merely preserving Ptolemy. They are actively rebuilding pieces of his mathematical machinery. Other scholars continue this critical tradition. Ibn al-Shatir, working in 14th century Damascus, develops planetary models that eliminate some problematic Ptolemaic devices while remaining broadly geocentric. Centuries later, mathematical similarities appear between certain Islamic models and those used by Copernicus. How exactly that knowledge may have traveled remains uncertain. Historians continue debating possible transmission routes, manuscript connections, and whether mathematical techniques reached Renaissance Europe directly or emerged through more complicated intellectual pathways. The resemblance is intriguing. The evidence for every step is incomplete. History rarely provides a tidy delivery receipt. Farther east, another extraordinary observatory rises during the 15th century at Samarkand under the ruler and astronomer Ulugh Beg. There, a monumental instrument is constructed for precise positional astronomy. You walk beside masonry built around an enormous measuring arc. The scale itself improves precision. without a telescope. Increasing the size of an angular instrument can make smaller differences easier to determine. Human eyesight remains limited, but architecture becomes part of the measuring device. Ulugh Beg and his collaborators produce an important star catalogue and astronomical tables. The stars mapped by Hipparchus and Ptolemy are being measured again. They have not changed much. Human precision has. Meanwhile, astronomical scholarship continues developing in medieval Europe. Universities emerge. Ancient texts circulate through translations, and scholars encounter both Greek astronomy and works transmitted through Arabic intellectual traditions. Ptolemaic cosmology becomes deeply established within education. Yet there is no single medieval European opinion about every celestial question. Philosophers debate details concerning celestial physics, Earth's properties, and possible motions. Even speculative alternatives occasionally appear. They do not overturn geocentrism. Why would they? You still lack decisive observational evidence showing Earth's motion. Stellar parallax remains undetectable. Aristotelian physics continues offering explanations that feel compatible with ordinary experience. The old system bends remarkably well. That flexibility becomes both its strength and its weakness. When predictions disagree with observations, parameters can sometimes be adjusted. Mathematical refinements preserve useful results, while deeper physical questions remain unsettled. The universe still seems finite and ordered. Beyond the planets lies the realm of stars, apparently fixed relative to one another. Their distances remain essentially unknowable. No observer can yet recognize the Milky Way as one galaxy among countless others. No one has seen another galaxy clearly enough to establish what it is, and the universe itself remains without a measured history. Its first stars have already been dead for billions of years. Although humanity has no concept of stellar evolution, you know none of this yet. Instead, you stand beneath the Samarkand sky as a measurement is carefully taken. Cold night air touches your face, while stone beneath your hand releases the day's remaining warmth. The observer checks the angle. Another number joins the record. This patient work prepares the next disruption. By the 15th century, European scholars possess access to expanding mathematical traditions, improved astronomical tables, and renewed study of ancient sources. Ocean voyages also increase demands for reliable celestial knowledge. Then, in the following century, a Polish astronomer will reconsider an idea that once seemed unnecessarily extravagant. Perhaps Earth moves. The suggestion will not immediately destroy the old cosmos. At first, it will simply rearrange the circles. But once Earth is allowed to leave the center, the heavens will never feel quite as stable again. By the early 16th century, the old mathematical universe still works well enough to remain useful. Yet its machinery has become increasingly uncomfortable for astronomers seeking elegant relationships among planetary motions. You arrive in northern Europe beneath a cold evening sky, where Nicholas Copernicus spends years considering a different arrangement. He does not begin with a telescope. There is no dramatic moment when he looks through glass and suddenly watches Earth moving around the sun. His revolution begins more quietly, through mathematics, inherited astronomy, and dissatisfaction with aspects of existing planetary models. Copernicus places the sun near the center. Earth becomes a planet. It rotates once each day and travels around the sun approximately once each year. The moon continues orbiting Earth, while the other known planets circle the sun. That rearrangement produces an elegant explanation for retrograde motion. Imagine Earth and Mars moving around the Sun at different speeds. Earth follows the smaller orbit and travels more quickly. Eventually, you overtake Mars. During that period, Mars appears to move backward against the distant stars, much as a slower carriage can seem to drift backward when you pass it. Mars never actually reverses its orbit. Your changing viewpoint creates the appearance. A mystery that required complicated geometric description now gains a natural explanation through Earth's own motion. Yet Copernicus does not abandon circles. His system still relies upon combinations of circular motions because uniform circular movement remains deeply attractive within inherited astronomical thinking. Heliocentrism is therefore not instantly simpler in every calculation, nor is it immediately more accurate in every prediction. That matters enormously. You are asking scholars to accept a moving Earth without providing the kind of decisive observational proof later generations will possess. The familiar objections remain. Why do you not feel Earth's rotation? Why are birds not left behind? Why does a stone dropped from a tower land near its base? And where is stellar parallax? If Earth travels across an enormous orbit, nearby stars should appear to shift against more distant ones. Nobody can detect that shift. Copernicus must therefore accept that the stars are extraordinarily distant. The universe grows, not because anyone has measured its full scale, but because a moving Earth requires enough distance to hide the expected stellar displacement from existing instruments. Copernicus's major work appears in 1543, the year of his death. Its publication does not instantly transform Europe. Some astronomers appreciate heliocentric mathematics while remaining uncertain about its physical reality. Others reject Earth's motion for philosophical, physical, observational, or theological reasons. The debate is more complicated than science simply fighting religion. Different scholars accept different pieces. You might use Copernican calculations while declining to believe that Earth physically travels around the Sun. Astronomical models can be tools before they become worlds. Then an unexpected celestial event challenges another ancient assumption. In November 1572, a brilliant new object appears in the constellation Cassiopeia. You step outside beneath crisp northern air. The unfamiliar light is startlingly bright, eventually visible even during portions of daylight. At night, it competes with the brightest objects overhead. Today, you know it was a supernova. Tycho Brahe studies it carefully. If the object belonged to the nearby atmosphere, as older ideas about celestial perfection might encourage some observers to expect, its position should shift noticeably against the distant stars when viewed from different locations. Tycho detects no substantial parallax. The new light must therefore be extremely distant. Something has changed in the supposedly unchanging celestial realm. The heavens are becoming less perfect. Tycho is wealthy enough to build an extraordinary astronomical research center on the island of Hven, supported by the Danish crown. Imagine approaching Oranienborg as evening settles over the island. The air carries salt from surrounding waters and smoke from fires. Assistants move among large instruments while paper, ink, brass, and carefully divided scales fill working spaces. Still, there are no telescopes. Tycho's great achievement is naked-eye precision. He develops and uses enormous quadrants, sextants, and other instruments designed to measure celestial positions more accurately than earlier observers could routinely achieve. His measurements approach precision of roughly 1 arc minute under favorable circumstances. That is extraordinary for unaided eyesight. Tycho does not accept Copernicus's moving Earth. Instead, he develops a hybrid system. Earth remains stationary at the center. The Sun travels around Earth, while the other planets travel around the Sun. This arrangement preserves a motionless Earth while gaining some geometric advantages of heliocentrism. It is not foolish compromise, given the available evidence. Tycho's system provides a serious alternative. Stellar parallax remains invisible, while contemporary physics still struggles to explain terrestrial motion convincingly. Then the sky misbehaves again. A great comet appears in 1577. Tycho measures its position from different locations and concludes that it travels beyond the Moon. That creates trouble for traditional solid celestial spheres. A comet, apparently, passes through regions where rigid crystalline structures should prevent such movement. The celestial architecture begins dissolving. One by one, observations remove pieces of the old physical picture, although no complete replacement has yet arrived. Then Tycho dies in 1601. His enormous collection of planetary measurements becomes available to Johannes Kepler, a mathematician with a very different temperament and cosmic vision. Kepler wants to understand planetary order. He initially expects elegant geometrical relationships and spends years wrestling with Tycho's exceptionally precise observations of Mars. Mars refuses to cooperate. The discrepancy is small, but precision makes small disagreements dangerous. Kepler attempts to fit Mars with circular motion and finds that the model misses Tycho's observations by about 8 arc-minutes in a crucial comparison. He could blame the data. Instead, he trusts them. Those few arc-minutes help break an astronomical tradition lasting nearly 2,000 years. The orbit is not a circle. Kepler discovers that Mars follows an ellipse with the Sun positioned at one focus. The result is revolutionary. Planets also move faster when nearer the Sun and slower when farther away. Later, Kepler identifies a mathematical relationship connecting orbital periods with orbital sizes. The heavens acquire new rules. These rules describe planetary movement beautifully, but they do not yet explain what physically pushes or pulls planets along their paths. Kepler proposes ideas involving forces connected with the Sun. Although his physical explanations differ from later gravitational theory, the mathematics has moved ahead of the mechanism again. There is also a delightfully strange side to Kepler. He combines rigorous mathematical work with mystical interests, theological ideas, and attempts to find deep harmonies within the cosmos. Modern categories would have made his desk untidy. Historians still debate how to weigh these different motivations when explaining his discoveries. His astronomy emerged from a world where geometry, physics, theology, and cosmic harmony could coexist within one intellectual project. You should not separate them too neatly. As Kepler calculates, you can almost hear a pen scratching across paper in a quiet room. Candle smoke hangs faintly in the air. Outside, Mars continues its elliptical journey. It has always moved this way. The planet did not change when Kepler discovered the ellipse. Humanity merely found a better description of a motion occurring long before humans existed. That distinction is central to your journey. The universe keeps its history whether anyone understands it or not. By the early 17th century, Earth has become a plausible moving world. Planetary circles are breaking into ellipses, and rigid celestial spheres are losing credibility. Yet the decisive visual shock is still approaching. A small tube fitted with glass lenses is spreading through Europe. Soon, someone will point an improved version upward. For the first time, Your naked eyes will no longer determine the limits of the visible universe. In 1609, the instrument finally reaches the sky. You return to the historical moment where your journey first opened, but everything behind it now looks different. Thousands of years of observation have prepared humanity to understand why one small tube can become so disruptive. Galileo Galilei did not invent the telescope. Reports of practical spyglasses had already appeared in the Netherlands during 1608. Galileo learns of the device and rapidly constructs improved versions of his own. He turns them upward. Imagine standing beside him on a cool Italian night. Your fingers touch the hard wooden tube, while glass catches faint reflections from an oil lamp nearby. The field of view is frustratingly narrow. Keeping an object centered requires patience. The image can suffer from optical distortions that would horrify anyone accustomed to modern instruments. Then the moon enters view. It is not perfectly smooth. Light and darkness stretch across its surface in irregular patterns. Galileo interprets changing shadows as evidence of mountains, depressions, and rough terrain. The moon suddenly resembles a world. This creates philosophical discomfort because some inherited cosmologies emphasize a fundamental difference between imperfect Earth and more perfect celestial bodies. The telescope reveals something messier. Galileo estimates lunar mountain heights from the lengths of their shadows. Once again, geometry allows you to measure a place you cannot physically reach. Then he points the instrument toward Jupiter. In January 1610, several tiny points of light appear close to the planet. Their positions change from night to night. Eventually, Galileo realizes they orbit Jupiter. 4 moons are circling another world. This observation does not prove heliocentrism by itself, but it destroys the claim that everything in the heavens must revolve directly around Earth. There can be centers of motion elsewhere. The cosmos has acquired neighborhoods. Galileo observes Venus as well. Its phases become particularly important. Venus displays a sequence of phases that cannot be naturally accommodated by the simplest traditional Ptolemaic arrangement, where Venus always remains between Earth and the Sun. A sun-centered arrangement explains them readily. Tycho's hybrid system can explain them too. This is important. The telescope weakens traditional Ptolemaic geometry, but it does not instantly distinguish between every competing model. History remains inconveniently complicated. Galileo also observes sunspots. Dark features appear on the sun and change over time. Other observers study them during the same period, leading to disputes over discovery and interpretation. The sun itself appears mutable. The supposedly immaculate heavens are becoming populated by rough surfaces, changing features, and orbiting bodies. Even Saturn looks strange. Galileo's telescope cannot resolve its rings clearly. He describes an object appearing accompanied by unusual structures, which later observations will finally reveal as a magnificent ring system. Sometimes new instruments create mysteries before solving them. That pattern will return repeatedly. A larger telescope reveals fainter objects, but also exposes phenomena nobody expected. Radio receivers will eventually detect invisible cosmic signals. Space telescopes will discover galaxies from astonishingly early eras. Gravitational wave detectors will hear collisions without using light at all. Each new sense enlarges the universe. For Galileo, however, the immediate consequences are already profound. The Milky Way becomes especially revealing. To your naked eye, it appears as a pale, luminous band through the telescope. Portions of that glow resolve into enormous numbers of faint stars. The sky contains far more stars than ordinary vision suggests. You begin to sense an uncomfortable possibility. Human eyesight has never shown you the complete heavens. Reality exceeds your biological equipment. Yet telescopic evidence does not end disagreement. Some observers initially distrust the instrument. Optical devices can create distortions, reflections, and false appearances. How do you know a mysterious spot belongs to Jupiter rather than the glass? Repeated observations help. Different telescopes help. Other astronomers confirm many discoveries. Still, interpretation remains contested. Galileo becomes a forceful advocate of Earth's motion and enters increasingly serious disputes involving philosophy, astronomy, biblical interpretation, and institutional authority. In 1633, the Roman Inquisition finds him vehemently suspected of heresy and requires him to abandon his defense of heliocentrism. The episode later becomes a symbol of conflict between science and religion. The actual history is more layered. Personal rivalries, institutional politics, theological questions, standards of proof, and Galileo's argumentative style all contribute to the confrontation. Historians continue debating the relative importance of these factors. What matters astronomically is that observations cannot be returned to darkness. Other telescopes are already pointing upward. Johannes Kepler, meanwhile, has supplied mathematical laws describing planetary orbits. His planets follow ellipses rather than perfect circles. Galileo develops another crucial piece of the puzzle through studies of motion. He investigates falling bodies and acceleration while challenging important aspects of Aristotelian mechanics. The familiar objection to a moving Earth begins weakening. Why does a dropped stone not land far behind you if Earth moves? Because motion can be shared. Imagine standing below deck inside a smoothly moving ship. An object dropped from your hand continues sharing the ship's horizontal motion. It does not smash backward into the wall. This principle helps make a moving Earth physically imaginable. You no longer require the planet to be stationary merely because ordinary objects behave normally upon its surface. But one question remains enormous. What keeps planets in orbit? Kepler can tell you how planetary speed changes. Galileo can transform terrestrial motion. Neither provides the complete universal mechanism. The answer begins taking shape later in the 17th century. Before reaching it, pause beneath another telescope. You smell damp grass and cool night air. Your cheek rests near the instrument, while one eye adjusts to the darkness. A bright point becomes a disk. A pale blur becomes many stars. The transformation seems almost magical, although it is simply glass redirecting light. Telescope design improves rapidly. Refracting telescopes become longer as astronomers attempt to reduce optical problems. Some instruments grow almost absurdly cumbersome. One 17th century design could involve extremely long focal lengths, with observers struggling to align separated optical components. Astronomy occasionally resembles an argument between human curiosity and inconvenient hardware. Then reflecting telescopes offer another path. Instead of relying only on lenses, they use mirrors to collect and focus light. In 1668, Isaac Newton constructs a practical reflecting telescope. Newton is already thinking about light itself. His experiments show that white light can be separated into colors using a prism. This will eventually help lead astronomy toward spectroscopy, although that transformation lies much farther ahead. For now, Newton is pursuing an even deeper connection. He knows Kepler's planetary laws. He studies terrestrial motion. He considers the moon. What if the force pulling an apple toward Earth belongs to the same physical principle guiding the moon around the planet? The familiar apple story is probably embellished through later retelling, although Newton himself recalled seeing a falling apple and thinking about gravity. The important part is not the fruit. It is the unification. For most of human history, the heavens and earth could seem governed by fundamentally different rules. Newton is about to erase that boundary. The moon will no longer require a special celestial physics. Mars will no longer move according to a separate heavenly principle. A stone falling through your hand and a planet traveling through darkness will belong to one mathematical universe. You look upward once more. Jupiter's moons continue circling exactly as Galileo saw them. Venus moves through its phases, and the rough moon crosses the same ancient sky watched by Babylonian observers. The objects have not changed. Your ability to see them has, and now the telescope has delivered enough evidence for the next great question. If earth and heaven obey the same rules, perhaps one force can connect them all. By the late 17th century, the heavens have become crowded with discoveries. Yet one enormous problem remains. You know that planets follow elliptical paths around the sun. You know their speeds change systematically as they move through those paths. You also understand terrestrial motion better than earlier generations did. But why should an orbit exist at all? You enter England during the years when Isaac Newton is developing an answer. The surroundings are ordinary enough, filled with damp fields, wooden rooms, candle smoke, paper, ink, and cold winter air. The question is anything but ordinary. Newton begins connecting mathematical ideas that had previously belonged to different worlds. Imagine holding a stone above the ground. You release it. The stone accelerates downward because Earth attracts it. Now imagine throwing that stone horizontally with increasing speed. A gentle throw carries it a short distance. A stronger throw carries it farther before gravity brings it to the surface. Newton realizes that, in principle, an object launched quickly enough could continuously fall while Earth's curved surface falls away beneath it. It would orbit. The moon becomes understandable in the same way. It is falling. It simply keeps missing Earth. This is one of the most beautiful conceptual changes in scientific history. Something apparently celestial becomes an extension of ordinary motion. The boundary between heaven and earth begins disappearing. Newton publishes his great work on motion and gravitation in 1687. His laws describe how forces change motion, while his gravitational theory proposes that masses attract one another. The strength of that attraction depends upon mass and distance. The same mathematical relationship can describe a falling object, the moon's orbit, and planetary movement around the sun. You now inhabit one physical cosmos. Kepler's elliptical orbits are no longer isolated mathematical patterns. They can emerge naturally from gravitational attraction combined with motion. The sun pulls Earth inward. Earth's existing motion carries it forward. Together, these produce an orbit. You feel nothing resembling a celestial rope because gravity supplies the continuous inward acceleration. Earth also pulls upon the sun. The sun's greater mass means its resulting motion is much smaller, but the interaction belongs to both objects. Gravity is universal. That word changes everything. You can use observations made from one tiny world to formulate principles reaching across the solar system. A force measured here appears capable of governing distant planets. Still, Newton himself faces a difficult philosophical question. How does gravity act across apparently empty space? His mathematical theory predicts gravitational behavior with extraordinary success, but the deeper physical mechanism remains mysterious. Newton refuses to invent an unsupported explanation merely to make the mystery disappear. The equations work. The ultimate cause remains unsettled. That uncertainty is worth remembering, because scientific success does not require every deeper question to be solved simultaneously. Sometimes prediction arrives before explanation. Again, Newton's theory quickly becomes powerful because it can be tested against celestial motions. Astronomers calculate planetary interactions more carefully. Jupiter pulls on Saturn, while other planets disturb one another slightly from idealized two-body paths. These small deviations are not failures. They become information. If gravity is correct, neighboring worlds should perturb each other's motion. Increasingly, precise observations allow astronomers to compare those predicted disturbances with reality. The solar system becomes dynamically alive. There is no collection of isolated planets moving independently around the sun. Every massive body influences others. Although many effects are extremely small, even tides connect Earth with the heavens. Walk toward a quiet coast. You smell salt and wet seaweed, while waves move rhythmically across stones. Water rises and falls according to patterns linked primarily with the gravitational influence of the moon and sun. The sky is touching the ocean. Newtonian theory helps explain why. The same moon that guided ancient calendars now pulls differently upon different parts of Earth, contributing to tidal bulges across the planet. Something once treated mainly as a celestial clock becomes part of terrestrial physics. Astronomers begin applying this new framework everywhere they can. Comets provide a dramatic test. These objects had long inspired fear, fascination, and speculation because they appeared unexpectedly, developed glowing tails, and crossed the supposedly ordered heavens. Edmund Halley studies historical comet observations using Newtonian ideas. He notices that comets seen in 1531, 1607, and 1682 may represent the same object returning repeatedly. He predicts its return. Halley does not live to see the result. The comet reappears in 1758, close to the predicted period. A celestial visitor once treated as unpredictable has become a member of the solar system. Today you call it Halley's Comet. There is a quirky historical twist here. Humans had recorded appearances of this comet for many centuries without realizing those appearances belonged to one returning body. The object was periodic before anyone recognized the period. Nature does not wait for classification. Newtonian astronomy also encourages a new confidence in prediction. If celestial bodies obey universal mathematical laws, then sufficiently accurate observations should reveal future positions. You can calculate eclipses. You can refine planetary tables. You can predict cometary returns. The heavens begin to resemble a vast clockwork system. That image becomes culturally powerful during the 18th century. Yet it can also mislead. The solar system is more complicated than a perfectly simple mechanical clock. Multiple gravitational interactions create difficult mathematical problems, and exact long-term predictions can become challenging. Later mathematics will reveal forms of dynamical instability and chaos within apparently deterministic systems. Knowing the laws does not always make calculation easy for 18th century astronomers. However, Newton's framework is astonishingly successful. It also helps transform the meaning of unexplained observations. Suppose a planet does not appear exactly where calculations predict. Perhaps your measurements are wrong. Perhaps the gravitational theory needs modification, or perhaps something unseen is pulling the planet. That last possibility will eventually lead to one of astronomy's great predictive triumphs, the discovery of Neptune in the 19th century. Mathematics will point toward a world before a telescope confirms it. For now, telescopes themselves continue improving. Long refractors gather more light. Reflecting instruments develop despite technical difficulties with mirrors. Astronomers measure planetary positions and search for new objects. Then, in 1781, William Herschel notices something unusual. Through his telescope, one object does not look quite like an ordinary star. Further observations reveal that it moves. It is a planet. Uranus becomes the first planet discovered with a telescope in recorded history. The traditional visible solar system suddenly expands. Saturn is no longer the outermost known planet. Herschel did not begin that evening expecting to enlarge the solar system. He initially considered the object cometary. Discovery often arrives disguised. Herschel and his sister Caroline become deeply involved in observational astronomy. Caroline discovers comets and contributes substantially to astronomical work, while William constructs increasingly powerful telescopes. Their attention does not remain confined to planets. They begin examining the distribution of stars and mysterious cloudy objects scattered across the heavens. Some appear as clusters, others remain unresolved patches of light. The word nebula can cover many different objects because astronomers do not yet understand their true nature. Some are clouds within the Milky Way. Some are star clusters. Some are distant galaxies containing enormous populations of stars. But you cannot know that yet. The scale of the universe remains uncertain. Newton has unified its physics without revealing its dimensions. You stand beneath the 18th century sky, feeling cold air against your hands as a telescope slowly turns toward another faint object. Gravity now reaches from your feet to the planets. Comets return according to calculable paths. A new planet has appeared beyond Saturn, yet the pale band of the Milky Way still surrounds you like an unanswered question. The next transformation will come when astronomers stop asking only how worlds move and begin asking what the stars actually are. Light itself will become the messenger, and through that light, the universe will finally begin revealing its hidden chemistry. Distances, temperatures, and immense stellar depths. As the 18th century gives way to the 19th, the telescope begins changing from a celestial surveying tool into something more powerful. You can now ask questions that earlier astronomers could scarcely approach. What are the stars? How far does the Milky Way extend? Are those faint cloudy patches nearby objects? Or could some lie unimaginably far beyond your stellar surroundings? William Herschel attempts to map the Milky Way by counting stars in different directions. Imagine yourself beside one of his telescopes during a cold English night. Damp grass darkens beneath your shoes, while the smell of wet soil mixes with smoke from a nearby building. The telescope points slowly across the sky. You count, then you count again. Herschel assumes that stars possess roughly comparable intrinsic brightness and that his telescope can penetrate sufficiently through the stellar system. Those assumptions will eventually prove problematic. Interstellar dust hides distant stars, while stars themselves vary enormously in luminosity. Still, his project represents an extraordinary conceptual leap. You are trying to determine the shape of the Milky Way from inside it. This is rather like attempting to map an enormous forest while standing among the trees. Nearby trunks block distant ones, and your location makes perspective difficult. Herschel's early star counts suggest a flattened stellar system. The Sun appears relatively near its central region in his reconstruction, although later astronomy will place it far from the true galactic center. The Milky Way is becoming a physical structure, yet the cloudy nebulae remain mysterious. Some resolve into stars when observed with better telescopes. This encourages the idea that perhaps every nebula is simply a distant cluster awaiting sufficient magnification. Others stubbornly remain cloudy. In 1781, Charles Messier publishes an influential catalogue containing nebulae and star clusters that might otherwise be confused with comets. There is something charming about its original purpose. Many objects now admired through backyard telescopes were catalogued, partly because they were annoying distractions for a comet hunter. Astronomy can be wonderfully practical. One particularly intriguing object is the Andromeda Nebula, visible even without a telescope under sufficiently dark skies. You can see it as a faint smudge. Nobody yet possesses decisive evidence showing that this pale patch is another galaxy containing hundreds of billions of stars. Its true distance is almost impossible to imagine. The debate over such objects becomes increasingly important. In 1755, philosopher Immanuel Kant had already suggested that some nebulae might be enormous distant systems resembling the Milky Way. The phrase island universes later becomes associated with this idea, but speculation is not measurement. Astronomy needs better evidence. Fortunately, light itself is about to become an instrument. Newton had shown that white light can be separated into colors. During the 19th century, scientists discover that spectra contain patterns linked with particular chemical elements. You place a prism before incoming light. Instead of merely seeing a bright star, you spread its light into a spectrum. Dark and bright lines appear at particular wavelengths. These lines become fingerprints. Elements measured in laboratories on Earth leave characteristic patterns within light. When astronomers examine sunlight and starlight, corresponding signatures appear. The heavens contain familiar matter. Hydrogen exists there. So do sodium, calcium, iron, and other elements known on Earth. A profound ancient division weakens again. Stars are not made from some completely separate celestial substance. Their light reveals chemistry shared with the material world around you. One famous exception initially seems to point the other way. During observations of a solar eclipse in 1868, astronomers detect a spectral line that does not match known terrestrial elements. A new element is proposed from sunlight before being isolated on Earth. You know it as helium. For once, humanity discovers an element in the sun before finding it on its own planet. The sky has become a laboratory. Spectroscopy also allows astronomers to investigate stellar temperature and motion. When spectral lines shift slightly toward longer or shorter wavelengths, the effect can reveal motion along your line of sight. Light carries velocity information across enormous distances. You do not need to chase the star. The star tells you how it moves. Photography adds another transformation. Early astronomical photographs are difficult because photographic materials are insensitive, and telescopes must remain accurately pointed for long exposures. Gradually, techniques improve. A photographic plate can collect faint light for much longer than your eye can effectively accumulate it. Objects invisible during direct viewing begin emerging. The universe grows richer. Photography also creates permanent records. Instead of relying entirely upon drawings or written descriptions, Astronomers can compare images made years apart. A transient object can be captured. A star's position can be measured later. Entire regions of the sky can be surveyed systematically. The observer's memory becomes less important. Meanwhile, distance measurement begins advancing through an effect ancient heliocentric astronomers had failed to detect. Stellar parallax finally appears. In 1838, Friedrich Bessel announces a successful parallax measurement for the star 61 Cygni. You have waited nearly 2,000 years for this. As Earth moves around the Sun, a nearby star appears to shift slightly against more distant background stars. The angle is tiny. That tiny angle reveals an enormous distance. 61 Cygni lies more than 10 light-years away. Even nearby stars are astonishingly remote. The absence of detectable parallax in antiquity was therefore not evidence of a stationary Earth. The stars were simply much farther away than ancient observers could measure. An old objection collapses through improved precision. This pattern should now feel familiar. A question can remain unresolved for centuries because the necessary instrument does not yet exist. Better measurements change what arguments are possible. The 19th century also witnesses a remarkable gravitational prediction. Astronomers notice that Uranus does not move exactly as expected. Perhaps another planet is disturbing its orbit. Mathematicians Urbain Le Verrier and John Couch Adams independently calculate where such a world might be found. In 1846, observers in Berlin identify Neptune near the predicted position. An invisible planet has betrayed itself through gravity. Newton's universe appears triumphant. Yet another puzzle grows stronger. What powers the sun? Coal cannot explain its immense energy over geological timescales. Gravitational contraction offers more energy, but still creates tensions with emerging estimates for Earth's age. The solution will require physics that does not yet exist. Stars hide nuclear furnaces. You are not ready to understand them. There is another unresolved problem involving the Milky Way. Astronomers debate its true size, structure, and the Sun's location within it. Interstellar dust complicates optical observations, hiding large regions behind dark clouds. Those dark patches once inspired curious interpretations. Some observers wondered whether they might represent genuine holes in the stellar distribution. Later, astronomy reveals that many are enormous clouds of dust blocking background starlight. Sometimes darkness is an object too. By the end of the 19th century, astronomy has changed almost beyond recognition. You can measure stellar distances. You can analyze the chemistry of stars. You can photograph objects too faint for ordinary vision. You can infer motion from spectral lines and discover planets through gravitational disturbances. But the largest question remains open. What exactly is the universe? Perhaps the Milky Way contains nearly everything. Perhaps the mysterious spiral nebulae are smaller structures inside it. Or perhaps each spiral is another immense stellar system, separated from you by distances that would dwarf even the newly measured spaces between nearby stars. Astronomers do not yet know. Soon, new physics will transform gravity itself. Larger telescopes will resolve individual stars inside distant nebulae, while variable stars will provide a ladder for measuring previously unreachable distances. You stand at the edge of that transformation. A photographic plate rests nearby, carrying tiny dark marks made by ancient light. They seem insignificant, yet among such marks, astronomers will soon find evidence that the Milky Way is not the universe. It is only one galaxy, and beyond it waits a cosmos so enormous that even Newton's apparently timeless universe will begin to expand. As the 20th century begins, The universe seems larger than ever, but its true scale remains uncertain. You can measure distances to nearby stars, analyze their light, and photograph structures invisible to the unaided eye. Yet the spiral nebulae remain troublesome. Some astronomers suspect they are enormous stellar systems beyond the Milky Way. Others argue that they belong within a single vast galaxy containing essentially the entire visible universe. Before observation settled that argument, gravity itself changes. In 1905, Albert Einstein publishes his special theory of relativity. Space and time can no longer be treated as completely separate backgrounds shared identically by every observer. Measurements of distance and duration depend upon relative motion in carefully defined ways. Light occupies a special place. Its speed in vacuum remains constant for inertial observers, forcing familiar ideas about simultaneous events to become less absolute. This is already strange. Then Einstein goes further. He spends years trying to reconcile gravity with the new understanding of space and time. In 1915, he presents the completed form of general relativity. Gravity is no longer simply an invisible force pulling across space. Matter and energy affect space-time itself. Objects then move through that curved geometry. You can picture a planet following the straightest available path through curved space-time. Although familiar stretched fabric illustrations provide only imperfect analogies, the mathematics is richer than any rubber sheet. General relativity explains a small, unexplained feature in Mercury's orbit that Newtonian calculations had struggled to account for completely. Then comes a dramatic test. During the total solar eclipse of 1919, expeditions measure apparent stellar positions near the darkened sun. The observations are interpreted as supporting Einstein's prediction that gravity bends light. Newspapers make him internationally famous. The measurements were less simple than the popular legend suggests. Historians and scientists have examined the uncertainties, equipment, weather, and data analysis surrounding the expedition. Later observations confirm gravitational light deflection with vastly greater precision. Still, the cultural moment is extraordinary. The universe has acquired flexible geometry. Einstein's equations also create an unexpected problem. When applied to the cosmos as a whole, they naturally permit universes that change with time. Einstein initially prefers a static universe. He introduces a cosmological constant into his equations, allowing a stationary cosmic model under particular assumptions. The decision is often accompanied by a famous story, claiming he later called it his greatest blunder. The exact wording and historical reliability of that quotation remain uncertain. Reality is more interesting anyway. The cosmological constant will return many decades later when astronomers discover evidence for accelerating cosmic expansion. An idea introduced partly to hold the universe still will eventually become relevant to explaining why expansion speeds up. Meanwhile, theorists explore alternatives. Alexander Friedmann finds solutions to Einstein's equations describing expanding or contracting universes. Georges Lemaitre independently develops expanding models and connects them with astronomical observations. The mathematics is preparing for a changing cosmos. Observations must now determine whether nature agrees. At the same time, astronomers are still arguing about the Milky Way. In 1920, an event later called the Great Debate takes place in Washington. D.C. Harlow Shapley and Heber Curtis discuss the scale of the universe and the nature of spiral nebulae. Their positions are not simple packages of correct and incorrect claims. Shapley has helped demonstrate that the Milky Way is much larger than earlier models suggested, and that the Sun lies far from its center. Curtis supports the idea that spiral nebulae are external galaxies. Both possess pieces of the future picture. Neither has decisive evidence for everything. That evidence arrives through variable stars. Henrietta Swan Leavitt had studied photographs of variable stars in the Magellanic Clouds while working at the Harvard College Observatory. She notices a powerful relationship involving chief-eyed variables. The longer their brightness cycle, the greater their intrinsic luminosity. Once calibrated, this relationship becomes a cosmic measuring tool. If you know how luminous a star truly is, and compare that with how faint it appears, you can estimate its distance. A new rung appears on the distance ladder. Leavitt's work becomes foundational, although the institutional environment of her era gives her fewer opportunities and recognition than many male astronomers received. The universe expands through patient measurement again. Then Edwin Hubble uses the Large Hooker Telescope at Mount Wilson Observatory in California to study the Andromeda Nebula. Imagine climbing toward the observatory after sunset. Mountain air becomes cold and dry. Machinery moves softly inside the dome, carrying smells of metal, oil, and old wood. The enormous telescope turns. Photographic plates collect faint light. During the early 1920s, Hubble identifies Cepheid variables in Andromeda. Their brightness changes reveal the crucial fact: Andromeda is far too distant to lie within the Milky Way. It is another galaxy. The pale smudge visible to your naked eye contains an immense population of stars beyond your own galactic system. The universe becomes enormous almost overnight. Other nebulae prove to be galaxies as well. The Milky Way is no longer the universe. It is one galaxy among many. Then another pattern emerges. Vesto Slipher had already measured spectra from spiral nebulae and found that many showed substantial shifts toward longer wavelengths. These redshifts indicated recession under the prevailing interpretation. Hubble combines distance estimates with available velocity data. Working with Milton Humason and drawing upon earlier measurements, in 1929, Hubble publishes evidence for a relationship between galaxy distance and recession velocity. More distant galaxies generally recede faster. This relationship becomes known as the Hubble law, although the historical naming hides important contributions from Lemaitre, Slipher, Humason, and others. Modern astronomy increasingly recognizes that broader story. You now face a universe that is expanding. This does not mean galaxies are simply exploding outward through pre-existing empty space from one central location. On sufficiently large scales, cosmic expansion concerns the changing scale of space itself. There is no ordinary central point inside the observable universe from which everything visibly flees. From another distant galaxy, observers would see a broadly similar large-scale pattern. The discovery changes the question of cosmic history. If galaxies are generally farther apart today, then they were closer together in the past. Run the cosmic film backward. Distances shrink, matter becomes denser. Eventually, you are forced toward conditions radically different from the quiet galaxies surrounding you now. The universe may have a history. That idea is profound because many earlier scientific models had treated the cosmos as essentially eternal and unchanging on its largest scales. Now the heavens themselves evolve, yet disagreement continues. Some physicists explore an expanding universe with an extremely hot and dense early state. Others will later favor steady-state cosmology, in which expansion occurs while new matter continuously maintains an approximately unchanging large-scale appearance. Observations must decide. You step outside the observatory. Cold mountain air touches your face, while the Milky Way stretches overhead as it did for prehistoric observers. But its meaning has changed completely. It is no longer the whole cosmos. Beyond its stars lie Andromeda and countless other galaxies. While space-time itself evolves according to physical laws humanity has only recently learned to describe. You have discovered cosmic expansion. Now you must follow it backward. And when you do, the universe becomes hotter, denser, younger, and increasingly unfamiliar, until eventually even ordinary atoms can no longer exist. Once you accept that cosmic space is expanding, an irresistible question appears. What happens if you run the expansion backward? Imagine watching a film of the universe in reverse. Galaxies approach one another, great distances contract, and matter occupies an increasingly smaller volume. The universe becomes denser. It also becomes hotter. During the 1920s and 1930s, this possibility develops from mathematical curiosity into a serious cosmological idea. Georges Lemaitre argues that the expanding universe may have emerged from an extraordinarily compact early condition. He later describes an idea sometimes translated as the primeval atom. The language will change. The central intuition remains. The universe you inhabit today may have evolved from a radically different early state. This does not immediately convince everyone. An expanding universe does not automatically tell astronomers exactly what happened at the earliest moment. Measurements of galactic distances remain uncertain, while theoretical physics is still developing rapidly. There is another uncomfortable problem. Early estimates of the cosmic expansion rate sometimes imply a universe younger than certain geological estimates for Earth. That cannot be right. If your calculated universe is younger than the rocks inside it, somebody has clearly misplaced something important. The problem eventually eases as astronomical distance measurements improve. This is another reminder that cosmology depends upon measurement as much as imagination. Then nuclear physics enters the story. By the 1940s, researchers understand far more about atomic nuclei than astronomers of Hubble's generation did. George Gamow and collaborators, including Ralph Alpher, investigate whether an early hot universe could explain the chemical elements. The young cosmos becomes a laboratory. If temperatures were sufficiently high, ordinary atoms could not survive. Matter would instead exist as nuclei, electrons, radiation, and other particles interacting within an intensely energetic environment. As expansion continued, the universe would cool. Nuclear reactions could then build light elements. This process is now called Big Bang nucleosynthesis. It primarily produces hydrogen and helium nuclei, along with small amounts of deuterium, helium-3, and lithium. Heavier elements require other processes. Stars will eventually manufacture many of them. The early universe, therefore, does not emerge containing everything necessary for planets, oceans, mountains, or your own body. It begins chemically simple. Complexity comes later. There is a wonderfully famous historical joke connected with the 1948 paper by Alpher and Gamow. Gamow added physicist Hans Bethe as an author, although Bethe had not contributed to the work, creating the playful sequence Alpher, Bethe, Gamow. It sounded like alpha, beta, gamma. Even cosmology occasionally allows terrible academic humor. The underlying science is serious. A hot early universe should leave observable evidence. if the young cosmos once contained intense radiation, expansion should stretch that radiation toward longer wavelengths while lowering its temperature. Eventually, a faint background glow should remain throughout space. This prediction emerges in work by Alpher and Robert Herman, among others, but few astronomers pursue it immediately. Meanwhile, a competing cosmology gains prominence. In 1948, Fred Hoyle, Herman Bondi, and Thomas Gold developed steady-state models. The universe expands, but its large-scale appearance remains approximately unchanged through time because matter is continuously created. There is no dramatically hotter beginning. The cosmos has no privileged creation era. Hoyle becomes one of the model's most famous defenders. During a radio broadcast in 1949, he uses the phrase Big Bang while discussing the rival cosmology. The name survives. Whether Hoyle intended it primarily as mockery has been debated, and historians caution against oversimplifying his tone. Either way, the label becomes permanent. You now have competing universes. One evolves strongly from a hot, dense past. The other expands while maintaining an approximately steady, large-scale character. How do you choose? You look. Radio astronomy begins opening an entirely new window onto the heavens. Traditional telescopes collect visible light, but celestial objects emit energy across a much broader electromagnetic spectrum. Radio waves can pass through clouds and reveal phenomena invisible to optical instruments. Enormous antennas begin listening to space. You can almost hear machinery humming beneath a broad dish while wind moves across its metal structure. The air smells of damp ground and electrical equipment. The universe has become audible only after translation into human technology. Radio surveys uncover strange sources. Some correspond with remnants of exploded stars. Others eventually prove to be distant galaxies with extraordinarily energetic central regions. Quasars become especially surprising. They appear almost star-like in visible images, yet their spectra reveal enormous redshifts. Their energy output is astonishing. Later understanding connects quasars with matter falling toward supermassive black holes in galactic centers. The distant universe looks different from the nearby universe. That creates trouble for steady-state ideas. If the cosmos remains broadly unchanged through time, extremely distant regions, which you see as they existed long ago, should resemble the local universe statistically. Increasing evidence suggests substantial cosmic evolution instead. Then comes a quiet accident. In 1964, radio astronomers Arno Penzias and Robert Wilson are working with a large horn antenna in New Jersey. Their instrument detects persistent microwave noise. It seems to come from every direction. They investigate possible sources of interference, including equipment problems and material left by pigeons inside the antenna. The unwanted signal remains nearby. A Princeton group led by Robert Dick is preparing to search for radiation expected from a hot early universe. The two stories meet. The mysterious microwave background is recognized as cosmic. You are detecting ancient light. Today it is called the cosmic microwave background, or CMB. It fills the observable universe with radiation corresponding to a temperature of roughly 2.7 degrees above absolute zero. This light has traveled for more than 13 billion years. It does not come from the absolute beginning. Instead, it comes from a later moment when the universe cooled enough for electrons and nuclei to combine into neutral atoms. Before that transition, free electrons scattered photons repeatedly. The cosmos was opaque. Afterward, light could travel much more freely. Those ancient photons are still arriving. Hold that thought gently. When a microwave detector measures the cosmic background, it is receiving radiation released before any star like the Sun existed, before Earth existed, before the Milky Way acquired its present form. You are seeing a childhood portrait of the observable universe. The discovery strongly supports hot Big Bang cosmology. Steady-state theory does not disappear instantly, because scientific ideas rarely vanish the moment contrary evidence appears. Researchers examine alternatives. They test assumptions. They demand better measurements, but the balance shifts decisively. Later satellites transform the background glow into a precision tool. NASA's COBE mission measures its spectrum with extraordinary accuracy and detects tiny temperature variations across the sky. OMAP later maps these variations in greater detail. The Planck spacecraft improves the measurements further. The background is almost uniform. Almost. Those tiny irregularities are crucial. They represent slight differences in density within the early universe. Gravity will amplify such differences over immense spans of time. Denser regions attract more matter. Structure grows. Eventually, the faint variations visible in the microwave background become connected with the formation of galaxies, clusters, stars, planets, and observers. The smooth early cosmos contains the seeds of everything later, yet a profound mystery remains. The Big Bang model describes an early, hot, dense, expanding state extraordinarily well. It does not simply describe an explosion occurring at one location inside empty space. Space itself participates in cosmic expansion, nor does the theory, by itself, provide a complete description of an absolute beginning from nothing. As you push equations toward the earliest conditions, established physics becomes increasingly uncertain. General relativity points toward extreme states where quantum effects should become essential. You need theories not yet complete. Cosmologists therefore begin asking about inflation, quantum fields, matter-antimatter asymmetry, and the origin of primordial fluctuations. The cosmic story has reached a boundary. Behind you lies recorded human history, telescopes, galaxies, and ancient microwave light. Ahead lies an era without stars, without planets, without atoms. To travel farther backward, you must enter a universe so young that matter itself has not yet taken the forms you recognize. You have followed ancient light backward until familiar structures disappear. There are no galaxies here. There are no stars, planets, oceans, stones, or living cells. Even ordinary atoms eventually cease to exist as you move deeper into the universe's early history. You are approaching the limits of established knowledge. Modern measurements place the age of the universe at roughly 13.8 billion years. That number comes from combining observations with a cosmological model describing expansion. Matter, radiation, and other cosmic ingredients. It is impressively precise, yet precision should not be mistaken for complete understanding. If you continue backward toward the earliest conceivable instant, current theories eventually become inadequate. General relativity describes gravity extraordinarily well on large scales, while quantum physics governs microscopic phenomena under extreme early conditions. You need both. A complete experimentally confirmed theory of quantum gravity remains unavailable, so your journey must become careful. Popular descriptions sometimes imagine the Big Bang as a tiny object exploding into surrounding darkness. That picture is misleading. The standard cosmological model describes an early universe that was extraordinarily hot and dense, followed by expansion and cooling. It does not require a central explosion point inside pre-existing empty space. Every sufficiently large region participates in expansion. Ask what happened before the earliest reliably described physical stages, and the answer becomes uncertain. Some theoretical models explore beginnings. Others permit earlier phases. Certain ideas involve quantum creation, bouncing cosmologies, or larger structures beyond the observable universe. None currently possesses enough evidence to become established history. Uncertainty belongs here. Now move slightly forward from that unknown boundary. Many modern cosmologists investigate a hypothetical period called cosmic inflation, during which space may have expanded extraordinarily rapidly during a tiny fraction of the universe's first second. Inflation helps explain several puzzles. The observable universe appears remarkably uniform across regions that would otherwise seem difficult to bring into causal contact using simpler early models. Its large-scale geometry also appears close to spatially flat. Inflation can naturally produce both features. Quantum fluctuations during inflation may also have been stretched to enormous scales, providing seeds for later cosmic structure. This is a beautiful idea. It is also incomplete. There are many inflationary models, and physicists continue debating which, if any, describes nature accurately. Evidence supports several predictions associated with inflation, but a unique underlying mechanism has not been established. The earliest universe remains partly hidden behind theory. As expansion continues, temperatures fall. The cosmos contains an energetic mixture of particles and radiation. Quarks, electrons, neutrinos, photons, and other particles interact rapidly in conditions far beyond anything you experience naturally today. You would not hear anything. Sound requires a medium and conditions suitable for pressure waves reaching an ear, and you possess neither body nor safe observation platform here. Still, imagine the atmosphere metaphorically. Everything is energy, collision, transformation, and expansion. The universe cools relentlessly. Quarks become bound into composite particles, including protons and neutrons, as conditions change. Within the first few minutes, temperatures become suitable for primordial nuclear reactions. Protons and neutrons combine. Helium nuclei form. Small quantities of deuterium, helium-3, and lithium also emerge. Most ordinary matter remains hydrogen nuclei. Then nuclear reactions largely cease as expansion lowers density and temperature. The universe is only minutes old. It already contains a chemical signature that astronomers can test billions of years later. Measurements of primordial light element abundances broadly support this picture. Although lithium presents a persistent puzzle, predicted primordial lithium abundance does not perfectly agree with values inferred from certain old stars. Researchers continue investigating whether the discrepancy reflects stellar physics, observational complications, nuclear processes, or something more fundamental. Even successful cosmology keeps loose threads. Then comes a long wait. For hundreds of thousands of years, the universe remains filled with hot plasma. Electrons move freely rather than remaining attached to nuclei. Photons repeatedly scatter from those charged particles. Space is therefore opaque, rather like looking through extremely dense fog. There are no transparent skies. There is no darkness either in the familiar sense. Radiation fills everything. Expansion gradually stretches wavelengths and reduces temperature. Around 380,000 years after the hot early phase began, conditions become cool enough for electrons to remain bound to nuclei more effectively. neutral atoms form. Hydrogen dominates. Photons stop scattering constantly and begin traveling freely across enormous distances. This transition produces the ancient radiation you encountered previously. The cosmic microwave background is released. Of course, it was not microwave radiation then. Expansion stretches its wavelengths over billions of years until you detect it today at microwave frequencies. You are receiving light transformed by the growth of cosmic space. The universe now becomes transparent and dark. No stars have formed yet. Imagine this strange interval. Hydrogen and helium spread through expanding space. Tiny variations in density remain from much earlier conditions. There are slightly denser places. There are slightly emptier places. Gravity begins working patiently. Matter flows toward denser regions. Dark matter, whose nature remains mysterious today, plays an essential role in modern models of this structure formation. You cannot see it directly through emitted light. Its gravitational influence becomes apparent through many observations, including galaxy motions, gravitational lensing, galaxy clusters, and cosmic structure. The name sounds theatrical. It simply reflects ignorance. Dark matter is called dark because it does not interact with light in the ordinary, luminous manner, and its fundamental particle identity remains unknown. Researchers have proposed many candidates. None has yet been conclusively identified as the dominant cosmic dark matter. This invisible component helps build gravitational scaffolding. Ordinary gas gathers within growing concentrations of matter. The universe enters what astronomers call the cosmic dark ages. The phrase is wonderfully dramatic. It refers to a period after the cosmic microwave background was released, but before the first stars illuminated the cosmos. You drift through hydrogen darkness. There is no familiar smell because there are no noses, atmospheres, forests, or oceans. There is no warmth against skin because you have no body here. Your imagined senses become useless. Only physics remains. Millions of years pass. Gravity slowly amplifies the ancient density differences. Gas accumulates inside growing structures dominated by dark matter. Clouds become denser. Their internal temperatures and pressures change. Eventually, somewhere within the young cosmos, gravity compresses primordial gas enough to ignite nuclear fusion. The first stars appear. Exactly when and how the earliest stellar populations formed remain active research questions. Current observations and simulations continue narrowing the possibilities, while the earliest individual stars remain difficult to observe directly. They were probably unlike the Sun, with almost no elements heavier than helium available initially. The first generation of stars likely formed under different conditions from many later stars. Some may have become extremely massive. They burn brilliantly. Their lives can be brief. Inside their cores, hydrogen fuses into helium, releasing energy that pushes outward against gravitational collapse. For the first time since the ancient background radiation faded into infrared and microwave wavelengths, concentrated visible starlight illuminates the cosmos. The darkness begins ending. Those stars also transform their surroundings. Their ultraviolet radiation changes nearby gas. Their interiors begin manufacturing elements unavailable in significant quantities after primordial nucleosynthesis. Carbon, oxygen. Eventually, through multiple stellar processes and later generations, many heavier elements appear. The early universe could make hydrogen and helium easily. It could not directly make you. For that, the cosmos needs stars. You watch the first lights flicker inside growing islands of matter. Around them, the universe remains mostly dark. There is no Earth waiting nearby, no sun, no Milky Way in its modern form. Yet the ingredients of complexity have begun their long transformation. Gravity has taken tiny irregularities from the infant universe and turned them into places where stars can ignite. Now those stars will become cosmic furnaces. They will live, evolve, and return newly manufactured material to surrounding space. From that enriched material, later stars and planets can form. The universe has learned how to build complexity, and the next step will begin inside the hearts of stars. The first stars shine into a universe that has waited hundreds of millions of years for concentrated light. You cannot stand beside one safely. These stars are enormous furnaces, held together by gravity and powered by nuclear reactions deep within their interiors. Yet imagine watching from a great distance. Around you stretches an almost completely black cosmos. There are no familiar constellations, because the modern arrangement of nearby stars will not exist for billions of years. Then isolated points begin glowing. Gravity has gathered primordial hydrogen and helium into increasingly dense clouds. As material collapses, its central regions become hotter and more compressed. Eventually, nuclear fusion begins. Hydrogen nuclei combine through sequences of reactions that ultimately produce helium while releasing energy. A star is born. The exact character of the first stellar generation remains uncertain because astronomers have not securely observed an individual pristine first-generation star. Simulations suggest that many may have been considerably more massive than the Sun. Researchers still debate their typical masses and formation environments. The answer matters. A star's mass largely determines how it lives. Lower mass stars can consume their nuclear fuel with remarkable patience. Massive stars burn much faster, becoming brilliant but comparatively short-lived. Cosmic extravagance is expensive. Some early massive stars may survive only a few million years before reaching the ends of their lives. Inside them, however, something extraordinary happens. The hot early universe produced mostly hydrogen and helium, with small quantities of several other light nuclei. It did not produce abundant carbon, oxygen, silicon, or iron. Stars begin changing that. As a sufficiently massive star evolves, its central conditions allow increasingly advanced stages of nuclear fusion. Helium can contribute to the production of carbon. Further processes build oxygen and other heavier nuclei. In the most massive stars, successive burning stages create an increasingly complex internal structure. You can imagine layers inside the star. Different nuclear processes dominate at different depths, almost like nested furnaces operating under increasingly extreme conditions. Eventually, fusion involving iron group nuclei can no longer provide energy in the same helpful manner. The balance supporting the stellar core fails. The star's final evolution can become violent. A massive star may undergo core collapse and produce a supernova explosion, although the precise outcome depends upon its mass, composition, rotation, and other factors. The explosion sends enriched material into surrounding space. Elements forged inside the star escape. Other elements are produced or redistributed during explosive processes. Neutron star mergers will later prove important for creating many, especially heavy elements through rapid neutron capture. The origins of individual elements are therefore complicated. There is no single cosmic forge. Carbon in your body and iron in your blood participate in a history involving different stellar environments, while elements such as gold can emerge significantly through extreme events involving neutron-rich matter. The popular phrase that you are made of stardust is broadly correct. It is also wonderfully incomplete. Some of your hydrogen traces back to the early universe itself. Many heavier atoms pass through stars. Others may have been shaped by stellar explosions or collisions between compact remnants. You are made from several chapters of cosmic history at once. The universe begins recycling. Gas enriched by early stars mixes with surrounding material. Later clouds collapse from matter containing more elements heavier than helium. Astronomers collectively call these heavier elements metals, even when a chemist would object. Oxygen becomes a metal in astronomical terminology. Chemistry has learned to tolerate this. The presence of heavier elements changes how gas cools and fragments during star formation. Later stellar generations can therefore form under conditions different from those of the first stars. Around some stars, disks of gas and dust appear. Those disks will eventually become the construction sites of planets. But first, galaxies must grow. The tiny density differences you saw within the cosmic microwave background continue developing under gravity. Dark matter gathers into halos. Gas falls into these gravitational structures, cools, forms stars, and creates increasingly recognizable young galaxies. Small systems interact. Some merge, others pass nearby, and distort each other gravitationally. Galactic growth is not always peaceful. Imagine two young galaxies approaching over hundreds of millions of years. Stars themselves are so widely separated that direct stellar collisions remain relatively uncommon during many galactic mergers. Gas behaves differently. Clouds can compress, triggering intense episodes of star formation. Galactic shapes become stretched and distorted. Eventually, the systems may combine. The universe is building larger structures from smaller ones. This hierarchical growth produces groups and clusters of galaxies. On still larger scales, matter traces enormous filaments separated by comparatively empty voids. Together, they form the cosmic web. You could travel millions of light years along one filament and still remain within a structure only partly understandable from any local viewpoint. Gravity has transformed microscopic primordial irregularities into architecture spanning extraordinary distances. Observations now allow astronomers to study galaxies seen at many different cosmic ages, because light travels at a finite speed. Looking farther away also means looking backward in time. A galaxy 1 billion light-years away is not shown as it exists at your present moment. You receive old light at extreme distances. Telescopes become time machines. The principle is simple enough to feel almost ordinary now, but its consequence is profound. You never see the distant universe as it is everywhere simultaneously. You see layers of history. Modern instruments exploit this relentlessly. The Hubble Space Telescope, launched in 1990, observes above most of Earth's atmosphere, avoiding many distortions and absorbing effects that limit ground-based observations. Its deep-field images become especially influential. Astronomers point Hubble toward apparently unremarkable patches of darkness and collect light for long periods. The resulting images contain thousands of galaxies. Empty sky was never empty. Later observatories push farther. The James Webb Space Telescope, launched in 2021, uses a large segmented mirror and instruments especially sensitive to infrared wavelengths. Cosmic expansion stretches light from extremely distant galaxies toward the infrared. Webb, therefore, allows astronomers to investigate surprisingly early periods of galaxy formation. Some early results reveal luminous galaxies existing remarkably soon after the Big Bang. Researchers continue debating what these populations imply for models of early star formation and galaxy growth. The discoveries do not mean established cosmology has simply collapsed. They mean the details of early structure formation are being tested with observations unavailable to previous generations. The old pattern continues. A new instrument makes the universe slightly less comfortable. Meanwhile, black holes become central characters in galactic evolution. General relativity predicts objects whose gravity becomes strong enough that, within a boundary called the event horizon, outward paths cannot return to the external universe. The idea once seemed highly theoretical. Today, evidence for black holes comes from many independent observations. Stellar mass black holes can form from the evolution of massive stars. Far larger black holes occupy the centers of many galaxies. Some contain millions or billions of times the Sun's mass. When matter falls toward an actively feeding, supermassive black hole, it can form an extremely hot accretion disk. Friction and magnetic processes convert gravitational energy into enormous radiation output. This produces quasars and other active galactic nuclei. A region smaller than its host galaxy can outshine the surrounding stars. The darkness becomes brilliant. Exactly how the earliest supermassive black holes grew so quickly remains an active research problem. Some may have begun from remnants of massive early stars. Others might have formed through more direct collapse of enormous gas concentrations. Several pathways may operate. Once again, the earliest cosmic structures resist a single tidy story. Galaxies and black holes also influence one another. Energy released near an active galactic nucleus can heat or expel gas, potentially changing future star formation. Stars enrich galaxies. Galaxies feed black holes. Black holes reshape galactic environments. The universe has become interconnected on immense scales. Through all of this, expansion continues. Galaxies bound together by gravity can remain within groups and clusters, even while sufficiently distant regions become farther separated as cosmic space expands. Your own Milky Way develops through this long process. Its oldest stars preserve evidence from ancient stages of galactic history. Its disk grows. Generations of stars live and die. Heavy elements become increasingly available. Then, roughly 9 billion years after the hot early universe, an ordinary cloud within one region of the Milky Way begins collapsing. It contains ancient hydrogen. It contains helium. It also contains carbon, oxygen, silicon, iron, and many other products of earlier stellar generations. At its center, a new star begins forming. Around that star spins a disk. You know the star already. It is the Sun, and within the dusty material surrounding it, the cosmic story is about to become local. About 4.6 billion years ago, a cloud of gas and dust within the Milky Way began collapsing. You have finally reached your cosmic neighborhood. The material around you carries an extraordinary inheritance. Hydrogen and helium preserve the chemistry of the early universe, while heavier elements record generations of stars that lived and died long before the Sun existed. Gravity gathers the cloud inward. As it contracts, rotation becomes increasingly important. Most material concentrates toward the center, where pressure and temperature steadily rise. Around that growing center forms a flattened disk. You cannot smell the dust or feel its heat because no human body could survive here. Still, imagine the environment through the materials that will eventually become familiar. There is carbon that may enter living cells. There is silicon that may become rock beneath your feet. There is iron that may eventually circulate within human blood. At the center, conditions finally become sufficient for sustained hydrogen fusion. The Sun begins its long main sequence life. Around it, tiny solid particles collide inside the protoplanetary disk. Grains become larger aggregates, while repeated collisions and gravitational interactions build increasingly substantial bodies. Planetesimals appear. Some merge, some shatter, some are thrown into different orbits. Planet formation is not a gentle assembly line. The young solar system is dynamic. Near the hot inner sun, rocky materials dominate the growing terrestrial planets. Farther outward, colder conditions allow additional compounds to condense, contributing to the formation of giant planet cores and smaller icy bodies. The exact sequence remains an active research subject. Scientists continue debating how quickly the giant planets formed, how extensively their orbits migrated, and how those migrations reshaped smaller bodies. The modern solar system preserves clues rather than a perfect diary. Meteorites become especially valuable. Some contain primitive material dating from the earliest stages of solar system formation. By measuring radioactive isotopes, scientists can estimate ages with extraordinary precision. Stone becomes a clock. Earth grows through countless collisions. Its early history includes enough energy to melt and reorganize substantial portions of the young planet. Dense materials sink toward the interior. Lighter materials remain nearer the surface. A metallic core develops beneath rocky layers. Then comes a colossal collision. The leading model for the Moon's origin proposes that a large planetary body struck the young Earth. Material from the impact eventually contributed to forming the Moon. Details of this event remain debated. Researchers test different impact geometries and chemical constraints, attempting to explain the striking similarities between lunar material and Earth's mantle. Whatever the precise sequence, the Moon becomes a permanent companion. The object that once terrified ancient eclipse watchers is born from planetary violence billions of years before anyone exists to see it. Earth cools, a crust forms and changes, water accumulates at the surface, although scientists continue investigating how much came from Earth's original building materials and how much arrived through later impacts. The atmosphere evolves dramatically. Eventually, life appears. Exactly how non-living chemistry crossed into the first self-sustaining biological systems remains one of science's deepest unanswered questions. Evidence indicates that life existed on Earth more than 3 billion years ago, possibly earlier. The earliest record is difficult to interpret because ancient rocks have often been altered by geological processes. Researchers continue debating particular chemical signatures and microscopic structures proposed as evidence for extremely early organisms, yet at some point, chemistry becomes biology. Life begins changing the planet. For immense spans of time, organisms remain microscopic. Some develop photosynthetic processes that use sunlight and release oxygen. Atmospheric oxygen eventually rises substantially. This transformation changes Earth's chemistry and opens new evolutionary possibilities. Complex cells appear. Multicellular organisms evolve. Life diversifies through an enormous branching history containing extinctions, adaptations, accidents, and environmental changes. There is no cosmic guarantee that humans will appear. Then, very recently by cosmic standards. One lineage begins looking upward with unusual persistence. You return to the observer beneath the ancient sky. The circle closes. Human beings emerge from matter created by cosmic evolution. Then use that matter to investigate its own origins. Your eyes contain atoms forged through ancient stellar processes. Your brain runs on chemistry assembled from elements produced across different stages of cosmic history. Then that brain invents mathematics. It builds telescopes. It asks where everything came from. By the 20th and 21st centuries, your instruments extend far beyond visible light. Radio telescopes map cold gas, pulsars, distant galaxies, and the cosmic microwave background. Infrared observatories penetrate dust and study cool objects. Ultraviolet and X-ray telescopes reveal energetic environments largely hidden from human vision. Gamma-ray detectors observe some of the most violent events known. Astronomy becomes multispectral. Then it becomes something more. In 2015, the LIGO detectors make the first direct detection of gravitational waves from a merger between two black holes. Instead of collecting light, the instruments measure tiny distortions in space-time itself. You have gained another cosmic sense. Black holes can now reveal themselves through gravitational waves, even when their merger produces little detectable light. In 2017, gravitational waves from merging neutron stars are observed alongside electromagnetic radiation. Astronomers combine different messengers from one event. This helps confirm that neutron star mergers contribute to the production of heavy elements. Gold acquires a dramatic ancestry. The universe also reveals planets everywhere. Beginning with discoveries in the late 20th century, astronomers identify thousands of confirmed exoplanets orbiting other stars. Some are enormous worlds hugging their stars tightly. Others are rocky planets. Many systems look surprisingly unlike your own. The solar system is no longer the only known planetary family. The ancient question changes again. Instead of asking whether planets exist around other stars, you ask how common Earth-like environments might be. You search atmospheres for chemical clues. You listen for artificial signals. You investigate Mars, icy moons, and other environments within the solar system for evidence of past or present habitability. No confirmed evidence of extraterrestrial life has yet been established. The silence remains scientifically fascinating. Researchers debate how frequently life begins, how often intelligence develops, and how long technological civilizations might survive. With only one known inhabited planet, your statistics are painfully limited. One example is not much of a survey. Other mysteries are even larger. Ordinary atoms account for only a minority of the cosmic energy budget within the standard cosmological model. Dark matter reveals itself primarily through gravity. You see galaxies rotating in ways suggesting more mass than visible stars and gas provide. You observe gravitational lensing caused by unseen mass. Galaxy clusters offer additional evidence. Yet the fundamental identity of dark matter remains unknown. Then comes dark energy. During the late 1990s, two research teams studied distant Type Ia supernovae to measure cosmic expansion across time. They expect expansion to be slowing under gravity. Instead, the evidence indicates acceleration. The universe's expansion is speeding up. A cosmological constant provides the simplest widely used explanation within the standard model, although the deeper nature of dark energy remains uncertain. The old Einstein term has returned. Today, the standard cosmological picture describes a universe dominated by dark energy and dark matter, with ordinary matter forming only a comparatively small component. Everything you directly touch belongs to the minority. That should make the cosmos feel appropriately strange. Modern astronomy has also photographed the environment immediately surrounding supermassive black holes. The Event Horizon Telescope combines radio observatories across Earth using interferometry, effectively creating an instrument with planetary-scale resolving power. In 2019, the collaboration releases an image of the black hole environment in galaxy M87. In 2022, it presents an image associated with Sagittarius A, the supermassive black hole at the Milky Way's center. Humanity has moved from naked-eye star patterns to horizon-scale black hole observations. Yet the fundamental habit remains unchanged. You collect light. You compare patterns. You test explanations. You build better instruments when existing ones cannot answer the question. From a dark field beneath prehistoric stars, you have reached spacecraft, gravitational wave observatories, particle detectors, and telescopes operating across the electromagnetic spectrum. The universe has been discovered twice. First, matter evolved from simple beginnings into stars, galaxies, planets, chemistry, and life. Then part of that matter became conscious enough to reconstruct the story. But your reconstruction reaches only the present. The sun still has billions of years ahead. Stars will continue forming and dying. Galaxies will change. Cosmic expansion will continue. So your final journey must turn forward. You have followed the universe from ancient light to yourself. Now you must ask what happens when the stars begin going out. You have reached the present. But the universe has not reached an ending. Tonight, stars continue forming inside cold molecular clouds. Galaxies continue colliding. Black holes continue feeding. And planets continue moving around distant suns. The cosmos remains active, yet every process you have followed possesses a future, including the quiet star that illuminates your own world. The sun is roughly halfway through its main sequence lifetime. For billions of years, hydrogen fusion has supported its core against gravity. That balance cannot continue forever, because the available hydrogen within the central region is gradually being transformed. Roughly 5 billion years from now, the sun will enter a dramatically different stage. Its core will contract while surrounding layers expand. The sun will become a red giant. Its outer atmosphere will extend enormously beyond its present dimensions. Mercury and Venus will almost certainly be engulfed. Earth's precise fate is more complicated. Even before any possible engulfment, increasing solar luminosity will make the planet unsuitable for familiar surface life much earlier. Oceans will not remain indefinitely. The comfortable Earth beneath your feet is temporary. This may sound melancholy, but the timescales are almost beyond emotional comprehension. Human civilization has existed for only a tiny fraction of the sun's lifetime. Billions of years remain before its red giant phase. Eventually, the sun will shed much of its outer material into space. The remaining core will become a white dwarf. No dramatic supernova awaits it. The sun lacks sufficient mass for that fate. Instead, a small, dense, stellar remnant will remain, gradually cooling across immense stretches of time. Other stars follow different paths. Massive stars can end through core collapse, sometimes producing neutron stars or black holes. Low-mass red dwarfs consume their fuel extremely slowly. Some may continue shining for trillions of years. None has yet reached the end of its full natural lifetime, because the universe itself is only about 13.8 billion years old. The smallest long-lived stars are cosmic beginners, Future astronomy would therefore encounter objects that do not yet exist naturally today. Galaxies will change as well. The Milky Way and Andromeda are moving toward one another gravitationally, although newer measurements continue refining their exact future trajectories. A close encounter is expected on billion-year timescales, but the precise probability and geometry of a direct merger remain areas of continuing research. If they interact strongly, their structures could be transformed. Long stellar streams might stretch across space. Gas clouds could compress. Star formation could change. Yet individual stars would probably pass one another at enormous distances. Galaxies look crowded in photographs because their light overlaps across your line of sight. In three-dimensional space, stars are separated by extraordinary emptiness. The night sky of some distant future world could become spectacular during a galactic encounter. Nobody knows whether observers will exist to see it. Far beyond the local group, another process dominates the future. Cosmic expansion continues. Under the simplest interpretation of current observations, dark energy behaves approximately like a cosmological constant. If that continues indefinitely, expansion will keep accelerating. Distant galaxies not gravitationally bound to your local region will become increasingly remote. Their light will be stretched toward longer wavelengths. Eventually, many will pass beyond a practical observational horizon. A civilization arising unimaginably far in the future might see a much emptier cosmos. It could inhabit the descendants of the local group while lacking direct access to evidence from many galaxies you can observe today. Cosmology itself could become harder. You happen to live during an interesting observational era. The cosmic microwave background remains measurable. Distant galaxies remain visible. Stellar populations provide rich evidence about cosmic history. The universe has left its records scattered across the sky. Those records will not remain equally accessible forever. There is something quietly strange about that. Scientific evidence has a cosmic season. The future also depends strongly upon dark energy's true nature. If it is genuinely a cosmological constant, accelerated expansion continues in one particular manner. If dark energy changes with time, other possibilities emerge. Some hypothetical models produce more dramatic endings, while others allow very different long-term behavior. Current evidence does not justify choosing exotic futures simply because they sound exciting. The simplest widely supported scenario points toward continued expansion. This leads toward what is often called heat death. The name sounds more violent than the process. It describes an extremely distant state in which usable energy differences become increasingly scarce and organized processes become harder to sustain. Before that era arrives, stars gradually disappear. Gas available for new star formation becomes depleted, locked into remnants, expelled, or otherwise unavailable. The universe enters a long stellar decline. Red dwarfs continue glowing after brighter stars have vanished. Eventually, even they exhaust their fuel. White dwarfs, neutron stars, black holes, planets, and other remnants remain. The universe grows darker. Timescales become almost absurd. If protons eventually decay, as some speculative theories permit, ordinary matter could transform over enormous periods. No proton decay has been observed. Experiments provide strong lower limits on proton lifetime, so you must leave this part of the future uncertain. If protons are stable, remnants can persist differently. The distant cosmic story changes according to particle physics that humanity has not yet solved. Black holes also have futures. In the 1970s, Stephen Hawking showed that quantum effects allow black holes to emit thermal radiation. A black hole can therefore lose mass. For stellar and supermassive black holes, this evaporation is unimaginably slow. Large black holes could persist for periods vastly exceeding the current age of the universe. Eventually, under standard assumptions, they evaporate. The largest surviving structures fade. You are approaching timescales for which ordinary words become almost useless. Trillions of years seem enormous until compared with numbers containing dozens upon dozens of digits. Human history becomes effectively instantaneous. Even stellar history begins looking brief. Yet the future is not known with absolute certainty. Dark energy remains mysterious. Quantum gravity remains incomplete. The ultimate stability of matter is unresolved. Scientists do not know whether current physical laws remain sufficient for describing every stage across such extreme durations. The distant future is therefore an extrapolation. That is an important scholarly caution. Cosmologists can calculate consequences from existing theories, but confidence weakens when predictions depend upon unknown physics. Your journey ends with questions. That feels appropriate. Every earlier generation experienced the same thing. A Babylonian observer could predict celestial patterns without knowing that stars were distant suns. Ptolemy could model planets without knowing Earth moved. Kepler could discover elliptical orbits without possessing Newton's gravitational theory. Newton could describe gravity without knowing curved space-time. Hubble could observe expansion before anyone possessed today's precision cosmology. Your generation is no exception. You can map the cosmic microwave background with astonishing accuracy while remaining uncertain about inflation's fundamental mechanism. You can measure dark matter's gravitational influence while not knowing what particle, field, or phenomenon produces it. You can observe accelerated expansion without understanding dark energy's deepest nature. You can discover thousands of planets without knowing whether even one hosts life. Knowledge expands beside mystery. Perhaps future telescopes will identify gases in an exoplanet atmosphere that strongly suggest biological activity. Perhaps another instrument will reveal the particle nature of dark matter. Perhaps gravitational wave astronomy will expose previously inaccessible moments of cosmic history. Perhaps new physics will change your understanding of the earliest universe. Or perhaps some questions will remain unanswered for a very long time. You cannot know, but you know how the process begins. Someone looks upward. Someone notices a pattern. Someone records it. Another person returns years later with a better instrument. The universe does not become less beautiful when a mystery receives an explanation. Usually, the explanation reveals larger mysteries behind it. The moon becomes a world. The sun becomes a star. The stars become distant suns. The Milky Way becomes a galaxy. The galaxies become inhabitants of expanding space-time. And the atoms inside you become survivors of a history stretching almost 14 billion years. Now the journey can become quiet. You imagine yourself once more beneath an ancient night sky, far from electric lights. Cool ground rests beneath you, and the faint smell of wood smoke drifts through the darkness. Above, the Milky Way crosses the heavens in a soft river of light. You know what earlier observers could not know, yet you share their silence and their wonder. The stars move slowly overhead, while Earth turns beneath them. Somewhere beyond sight, galaxies continue drifting through expanding space. The universe has carried you from its earliest light to this small, peaceful moment. For now, there is nothing more you need to measure. You can simply look upward, breathe slowly, and let the ancient sky continue without you.